what is your plan for the observation delivered by LSST?
This was my question too. Because of course we are interested in this project, but we have it's not a formal plan yet, but of course we are interested to, but maybe more in help with the machine learning. Fabio is helping me with that, but we can discuss this later with Julian, maybe tomorrow in the discussion, because it's very interesting. Yes, it was my question, if we can talk after this, this talk.
I might not be available for the discussion tomorrow because kids, but I would be happy to discuss offline or later on. Yeah.
Okay.
Julia, you have said in your last sentence, one of the last slides, that you have a meeting the 8th, no, the 2, the 2nd of December. What is this meeting?
Oh, this is with Damien and Bertrand. I'm going. Going to CA. The purpose of that meeting is especially to discuss this link and trying to see what we need to design and implement for that.
Okay, no problem. I'm sure I will have some feedback quickly.
Yeah.
Okay, thanks.
Okay, thank you again, Julian, for this interesting talk.
Thanks.
Let's move on to the second talk by Benjamin Arsier. He is going to talk about detection of short high energy transients in the local universe with SVOM ECLAIR. Please, Benjamin.
Okay, can you see my screen? Can you hear me?
Yes.
Okay, perfect. So I will start. So hi everyone. So I'm Benjamin Arsier, I'm a third year PhD student working under the tutorship of Jean-Luc Attea, the PI of ECLAIR. And so today I'm going to present you like the detection of the short high energy transients in the local universe with this instrument. Okay, so just a brief overview. So I'm quickly going to talk about the SVOM mission, especially the ECLAIR instruments. I'm just going to explain how you can assess the performances of the ECLAIR instruments, even though it's still not flying via simulations. And finally, I will show you how you can apply this performances analysis on a specific subsample of short high energy transients that are from the local universe, and what the different synergy is with the gravitational wave observatories or like the other SVOM instruments can be very helpful to determine the nature of these events that we're observing. Okay, so this is SVOM, and as you can see, like you have 4 onboard instruments on top of it. So you have 2 gamma rays instruments that are used for the detection, for the spectral characterization, and for the localization of the gamma ray bursts. So these 2 instruments are ECLAIR and GRM. So GRM is not very good at positioning, but has a very wide spectral range, so it can be very useful to characterize the spectrum information. And on the other hand, ECLAIR has a smaller field of view and a smaller energy ranges, but is very good at finding the position, like an accuracy of a few arc minutes. So once ECLAIR and GRM have detected something, a gamma ray burst, the satellite is going to slew, and you're going to point the narrow instruments that are the VT and the MXT, and also like a VHF alert is sent on the ground, where you can point the ground telescopes, Colibri, CGFT, or GWAC, to try to look at the afterglow after like the host galaxy. They try to determine the redshift, for example. So everything is working on synergy, but at the beginning, what triggers everything is either a target of opportunity if you really have a location from another instrument, or most of the time it's a trigger from ECLAIR that is going to give you a rough estimate of the position. So just a bit of a close-up of ECLAIR. So what you have here are the main components of the instruments with the main lab that have participated to it. So in IRAP in Toulouse, we took care of the team took care of the DPIX and the electronics that is going to read the events that are incoming. And then these events are transmitted to the UGTS, which is the scientific trigger and control unit, that is going to take these events and run a trigger algorithm to try to see if a GRB is detected, and if it's the case, then send a message to the satellite that then is going to slew, etc. So the main characteristics of ECLAIR, you can find it here. So it's detecting between 4 keV and 120 keV. So this is a very important characteristics, because if you compare to SWIFT that is starting at 15 keV, these energy ranges allow the instrument to be more sensitive to high redshift GRBs, for example, where the prompt emission is going to be redshifted in like lower energy bands. It has a 90 times 90 square degree field of view. It allows roughly to detect, I think it's 55 GRB per year, something like this, 1 per week, basically, in order of magnitudes. Yeah, and it has a good localization accuracy and a good energy resolution. So and one of the characteristics of SVOM and ECLAIR that is very important, and that was not the case on former missions, is is that ECLAIR will send all the events that are recorded on board, the raw events, to the ground directly. And this is what is called the offline trigger that will be used by this. And it allows to reprocess the data on the ground. And so you have more time to analyze the data, you have more knowledge of the context, you have more calculation power, you can allow to have more false alert. And what it means is that you can be more sensitive than what you are on ground. And so you can analyze some events that you couldn't see with the onboard configure algorithm, for example. And the other main interest here is the offline analysis. Let's say that that's what is done for BAT for the moment with Guano, for example, where you have like a gravitational wave events, for example, that is happening sometimes, and you want to have like a limit of what the Swift BAT instrument has seen, and so you can reprocess the data to have a confident upper limit. Okay, pictures of ECLAIR that you have here. So you have the detection plane that has been assembled at CNES that you can see here with the thick 1400 detectors. And on top of that, you have the shielding around, I think Francois showed it yesterday, with the shielding and the COVID mask on top of it. So now the instrument has been tested at Airbus Defence and Space, and the testing is done. Okay, so now what I'm going to explain is to show you how we can simulate the performances of the instruments while it will be in space via simulations. And so this work during my PhD thesis is based on the work of several former PhD students that have performed individual work. And what I did is basically to gather the individual work from people to make it work together. Okay, so first of all, I just want you to understand what is basically the kind of things that ECLAIR is seeing. ECLAIR is recording what we call events. So an event is created when you have, for example, a photon that is arriving on the instrument at the time t and impacting a pixel xy and depositing an energy E. So it's 3 characteristics. And so when you're going to simulate some ECLAIR observations, what you're going to do is actually to simulate the distributions of time, energy, and position of these events. And so the first thing that is very important to simulate is the background from ECLAIR, because what you can see on the left is simulations of the field of view of ECLAIR. You can see that because of the anti-solar pointing in the low Earth orbit, the Earth is going back and forth in the field of view. It's very different from Integral or from Swift, because here you don't want to maximize the number of birds that you're going to detect every year, but the birds that you detect, you will have an optimal follow-up, because the portion of the sky that you observe at this moment on this side of the Earth, it's nighttime, so you can have a direct follow-up. The main impact of this is that since the Earth is going inside and outside the field of view, you can see on the right, on the light curve background that you have, that is synchronized with the left images, you can see that the background is strongly changing because of that. And so like you can see here, it's in terms of count, but also in terms of spectrum, you have different properties, because the main components of the background are the CXB, the albedo, the reflection, the particles, And so these components are changing relatively to the location of the Earth. So that was the work of Sujay Mate, that was a former PhD student at ARA, that worked with Laurent Boucher based on GeoInfor simulations to create a tool that allows from attitude fire orbits to generate the background, the estimated background. So we have the background. What is interesting now is to try to simulate the GRB on top of it to see how we can see that. And so this is a work that has been performed by Sarah Antier, Frédéric Dane, that is maintained by Maxime Bocquier and David Corr at IAP and CA. And so you start from existing spectrums and light curves, and you combine the two of them so you can draw some photons and simulate the GRB thanks to that within the ECLAIR bands and with the ECLAIR response matrices. So what you have here are an example of some of the GRB that have been simulated. And the main interest here is not only you can simulate it as it has been observed, but if you have access to the redshift, you can also simulate this same GRB at different redshifts and see, for example, up to which redshift you can see an object. This is very practical, for example, if you want to draw an horizon for some of the GRB, for example, 1708, 1708. And once you have the GRB photons and you have the background events, you gather everything together in one single events file, where you're going to apply the response matrices on the GRB photons, the response matrices on the sky X-ray sources that you can have based on the location where you look at in orbit. And you have an orbit like the one you can see on the right. So here, like as a good example, you can see in blue, you have the CXB. In yellow and green, you have the two other components that are the reflections in the albedo. On the brown, you can see the crab source that is rising and fanning behind the Earth. And you have here in green, in pink, GRB, very strong signal-to-noise ratio. The main idea here is that thanks to these simulations tools, you can basically simulate any situations that will happen in the sky. And what we are working on is also to try to add some instrumental effects that are observed on the detection plane to these simulations. Okay, so now that we know how to simulate some observations, I can show you how you can adapt it to a certain specific populations to make some science. So this is a paper that has been published last year in December 2020 with some co-authors from the ECLAIR consortium. So what we have tried to do is to get a local sample of GRB, I mean, short high energy transients that are detecting with a redshift below 0.3. So we have made like an inventory of the objects that you can have here. So you have 24 long GRBs, 10 short GRBs, 7 SGR giant flares. I will come back to definitions because to this after. And so for the long GRBs, you can subdivide them in subcategories, same for short GRBs. And so we have tried to gather like as many information as possible from it. For example, something that is very common is when you want to simulate a GRB that has a redshift, most of the time it's a swift-bat GRB. But since the energy range of swift-bat is very limited, most of the time the spectral characterization is very poor. You have a poor law for characterizing your GRB spectrum. And so in that case, what we try to use is to, if this specific GRB has also been observed by GBM, by Fermi, or by Integral, or by Conus-Wynne, then you take the spectrum that is as large as possible, because what is going to happen is if you take a single power law and you extrapolate this power law to low energy of ECLAIR, you might overestimate the number of photons that you're going to receive. So it's very important to try to keep a spectrum that is describing as much as possible the GRB. So with these GRBs and the properties, we can make several plots like the one that you have here. So what you have is the several categories. You have the low luminosity GRBs that are here. So the 1708, 1708, for example, is famous, 111005A also. You have the SGR giant flare that you can see here. And here you have also another one that has been classified as an SGR giant flare. But you can see that based on the EISO properties, the giant flare is quite different from what you expect from the other populations. So actually, this giant flare is more probably an analog of 1708, 1708. Maybe there are So there is a paper that has been written on it. Okay. You can also plot the amateur relation. That is quite interesting for local GRBs because this relation is working quite well for very distant GRBs. But for local GRBs, you can see that you have a part of the long GRB population that is completely out of this relationship. That might be because in the local universe, you have access to events that are not visible at higher redshifts. And so you can see that on this plot, like the energetic of most of the events is, I mean, 1 or 2 order of magnitudes below like the main energy that you can see on most of the GRBs in the universe. And so it might explain why the amateur relation is not verified here. You can see also that for the giant flare, it seems that there is something similar. So it has been published by Zhang in 2020. But I mean, this is yet to be confirmed because the sample is just 6 SVO giant flares here. Okay, so we have created our sample. We have tried to characterize it as much as possible by using the right light curve, the right spectral information. And so we have simulated with the method that I've shown you before. And now the point is you have your simulated events and you want to know whether ECLAIR will be able to see this particular GRB or not. And so what we've done is we have simulated the count trigger algorithm that will be on board of the instruments. And so based on the events that we feed to this count trigger, the count trigger is going to create some light curves at different time scales and different energy ranges. And so let's say at a given moment, like it is expecting a background noise of 3000 counts per second. Okay, so what it's going to do is to draw a light curve with a 1 second time scale, and imagine that the signal to noise ratio, so like the number of count that it's going to receive is above 3000, like 4000, for example. Then it's going to notice this difference, and it's going to save this particular. It's going to create a shadogram with this particular time scale and this particular energy ranges. And with this shadogram, it's going to operate the deconvolution with the mass pattern to get a sky image. And what happens is when you look at the sky image, if there is a new source in the sky image that has a sufficiently high signal to noise ratio, and that this new source is not part of a source that is already known, for example, then it says that the object is detected and that we have a new GRB. So the count trigger is in 2 steps, like light curves to get to detect an excess. And if this excess is high enough, you create an image. And if on this image you have also an excess, then you detect something. And so thanks to that, we can assess the detectability of our sample. And we know that 35 out of 41 GRBs are detected by the method. And so why is it important to detect these objects? So I'm going to talk briefly about 3 aspects that are also present in the paper. The first one is, of course, the multi-messenger astronomy with LIGO overview. What you can see here, for example, so the square that have a blank square inside are the long GRBs without any associated supernova. So these events have been detected. So you have 2 of them that have been detected in 26, one in 2011 and one in 2006, 2011 and 2004. And so these events are quite puzzling because the consensus was that long GRBs are associated with supernovae. And that's actually what we observe most of the time. But the problem is that you can observe the long GRBs up to very high redshifts, but the supernova is only visible up to redshift of 1 most of the time. And then you have observational constraints that most of the time prevents you from observing these objects. And so one that is very particular is that 111005A was very close to us. And still, there is no GRB that has been detected here. And what could be interesting with the multi-messenger astronomy is that if you detect something like this and you have or do not have any gravitational wave counterparts, it's interesting in both sides. You have, of course, 1708, 17A, like, I mean, a new detection of neutron star merger with the gravitational waves plus GRM, and maybe ECLAIR that is detecting it could be very interesting. And you also have, I know that the SVOM ground telescopes also are actively searching for counterparts for every gravitational wave events. And then you have something that is very interesting, that is due to the fact that now we are entering soon the 04 and 05 campaigns. So SVOM will be launched approximately 6 months after the beginning of the 04 campaigns. So normally we should expect approximately 1 year of coexistence between the 04 and the SVOM observations. So what you can see is that for up to 04 limits, the only gamma rays that you could expect are most of the time you don't have a volume that is sufficient enough to observe on-axis GRBs. So what you observe is off-axis GRBs most of the time, like the one that you have here. And for these GRBs, you are limited by gamma ray telescopes because they are very faint, and so you don't detect them very well if you observe too far away. But when you observe on axis, the thing is these GRBs are detected by the GRB detectors, but they are too far away from the gravitational wave detectors. And this is true until 05, where what you can see here, you have the limits for the neutron star, and neutron star black hole. You can see that you're starting to go at a redshift where you can see the first on-axis GRBs. So that could be very interesting for the coming year. The second one is the VT, the GWAC, the CGFT, and Colibri for the follow-up of the long and short GRBs, especially what I talked about the supernova-less long GRBs, because you will be able to perform observation to an air band magnitude of 24 approximately. And so that could trigger the interests of the science community, because imagine that you have a closed long GRBs and you have the redshifts and you do not see any supernova emerging, and you have actually deep observations with the VT and you still cannot see anything. It might be the opportunity for the science community to point like 8 meters telescope, for example, to really try to put strong constraints on the supernova luminosity. And the last one that we discovered is very linked to the offline trigger, is the detection of the SGR giant flares in the Virgo cluster. So giant flares are very short and very hard, which means that most of the time they can trigger the counter-ray trigger, but the image is very hard to make because you don't have a lot of photons. So the algorithm will not be able to create an image, and it will not be able to detect, to trigger on these SGR giant flares. And the thing we notice is we have observed only a few of them in the past 20 years, but they are all coming from galaxies with star formations that are relatively low. And the thing is, with the Virgo cluster, like you have access to many more galaxies and stars. And so the star formation rate as globally is way larger than the small galaxy where they have been detected. And it turns out that for some of the SGR giant flare, they could be actually detected in the Virgo cluster. You can see here in blue, you have the distance of the Virgo cluster and you have the signal to noise ratio. And you can see that some of the SGR giant flare could be detected in this Virgo cluster. So that could be very interesting because the Virgo cluster is going to be observed by MXT for the general program. So that could be the opportunity with the offline trigger to see if we can detect more SGR giant flare with the ECLAIR. So that's it. Thank you for your attention. If you have any question, feel free to ask.
Thank you, Benjamin, for your talk. Any questions? Please raise your hand. Please, Michael.
Yes, I have a question concerning what data are going to be sent down to Earth. Once ECLAIR is pointing to a given region of the sky for a GRB, for instance, there's likely to be more than one X-ray source in the field of view. Are then the other X-ray sources recorded and sent down also?
Oh, sorry, I didn't get the end. Several sources?
Yeah, if you point in any direction of the sky, you may have more than one X-ray source in the field of view. Not only the GRB where you are pointing to. So are the data from the other X-ray sources also recorded and sent down?
If you mean the events from the other source, yes, of course. Like you cannot select the event that you're going to detect. But what the algorithm does is when you're detecting something, it's checking whether the source is actually a new source. And the VHF message is only sent if the new source that is discovered is something, I mean, if it's the new source, if it's not a source that is already existing in the sky. But the data that are going to send by X-bands, if you mention, if you talk about, if you talk about this slide, like all the data are going to be sent because we have, I mean, we cannot know whether they are coming from X-ray source in the sky or from a GRB.
Okay, because you will see from my talk that I'm interested also in sources which are pre-existing but which are highly variable. You know?
Oh, and yeah, exactly. That's the main advantage of the X-band telemetry, and especially for the, I mean, the main problem is the X-band telemetry is that you have to go in front of an X-band station, which takes from few hours to 12 hours, I think. And so the thing is, for time-related observations, sometimes it can be problematic, but for your problem, I think it could be perfect because you receive the events, you know, you have a catalog of sources and you know the pointing of the instruments, so you know more or less the sources that are in the sky. Mm-hmm. So I think it's possible with the imaging part of the instruments, you can have access to the locations of the sources in the field of view. So it might be possible to disentangle more or less the flux from each of the sources.
Yeah, okay, thank you.
Okay.
More questions? Thank you again, Benjamin, for your interesting talk. The next speaker is